Hello, I'm Yong Kiam. I'm going to be telling you about joint work with Stefan and André that we did at Carnegie Mellon. And this work is about the study of switch system stability questions using informal methods. So as a quick introduction, we're interested in the study of hybrid systems because they allow us to understand the combination of discrete and continuous dynamics present in many real-world systems. For this work, we're interested in the study specifically of stability for hybrid systems. So to motivate stability a little, I want you to think about being in a car that's being driven by a cruise controller. So if you plot the velocity time graph of your car, you probably think of something that looks like this, where the car's initial velocity is somewhat close to the cruising velocity, then the cruise controller is going to drive the car closer and closer to the cruising velocity over time. So this is an example of what we would think of as a stable cruise controller. However, the other two plots I've shown on this slide, well, they aren't stable because, for example, in the middle plot, the cruise controller is driving the car, well, around the cruising velocity, but it never quite converges to the cruising velocity. While the one on the right, well, it eventually gets us to the cruising velocity, but it does so by transiently braking the car all the way down to a stop before speeding back up again. Neither of these would be something that we think of as a correct cruise controller. So the point is that stability is a key correctness criteria, especially when we are designing these systems, and they deserve proofs, again, especially if we are in a safety critical setting. In prior work, we investigated stability verifications for ordinary differential equations. And in this work, we're going to be interested in those stability questions for hybrid systems. Why are we interested in hybrid control in the first place? Well, it turns out that hybrid switching control can be used to achieve certain control objectives that cannot otherwise be achieved using purely continuous means. And here's an example of a cut where the controller can, well, just output values for either accelerating or braking the cut. And the objective is to swing up the pendulum into its inverted position. And it turns out that there must be a discontinuity in this controller, which is in order to invert the pendulum from all possible initial states, okay? And such a discontinuity can, for example, be introduced using the simple idea of switching between two different controllers, okay? However, switching also comes with its own set of challenges with respect to stability. So on the top row here, I've showed you two differential equations which are both individually stable. So the blue one sort of spirals towards the origin, similarly for the red one. However, it's possible to design, well, poorly design a switching mechanism such that if I apply this switching mechanism where the system sort of follows the red differential equation in this quadrant, and then the blue one, and the red one, and the blue one, and so on, the overall system is actually going to become unstable. You can see it sort of gets driven further and further away from the origin because of the switching signal. So the point is that, well, given a switching control design, we're going to want to be able to adequately justify the stability of that design. And of course, in the controls literature, there are many different justifications for different switching designs. But the question now is, well, what if I want to come up with my own switching design, or if I want to combine some of these switching designs, how do I go about doing that in a trustworthy and correct way? Okay, and this work provides an answer to that by combining ideas from controls and verification towards switch system stability verification. From controls, we're going to take switching mechanisms, and we're going to model that using the language of hybrid programs from verification. From controls, again, we're going to take stability concepts. Specifically, we're going to take uniform global pre-asymptotic stability, and we're going to specify that formally using differential dynamic logic, or DL for short. Now, from controls, again, we're going to take proof ideas for stability, namely the concept of common or multiple Lyapunov functions, and we're going to see formally how that can be understood using the classical idea of loop invariants from verification. And thanks to this formalization, now we can take examples and case studies from controls, and we can now verify stability for those examples using the KeYmaera X tool for hybrid systems proving, which is based on DL. Okay, so let me give you a bit of background on switch systems and hybrid programs. Mathematically speaking, a switch system consists of a family of differential equations, x prime equals to fp of x, and a set of switching signals, sigma. Okay, sigma here in this context are going to be piecewise constant functions, So intuitively here in this picture over here, sigma is going to prescribe the modes that the switch system is going to be in at each time interval. So in this example, it prescribes mode 1 in this interval, and then mode 3, and then mode 2, and so on. Accordingly, what the switch system is going to do, it's going to follow the first mode until the first switching time, and then the third mode until the next switching time, and so on and so forth. You can think about this as a mathematical abstraction of a system that's undergoing controlled switching. So for example, we have a continuous plant and a set of continuous controllers and some kind of design controlled switching logic, which decides which of these controllers to apply on each time interval. Now, the other ingredient we're going to use is the language of hybrid programs from differential dynamic logic. And I'm showing you the full language here, but I'll show you an example of this in the next few slides. So the essential idea of a hybrid program is that it allows us to seamlessly combine continuous and discrete dynamics, where the continuous dynamics is specified by a differential equation, and the discrete dynamics just uses the usual constructs of programming languages like assignments, tests, composition, choice, and even looping. Okay. Given a hybrid program model alpha, we can also write down properties that we expect to be true of that program alpha, and later on we can prove these properties. So for example, we can write down, well, is it the case that a certain variable is greater than or equal to 0? And we can write down, what is it the case that formula phi and a formula psi are both true? We can express, for example, is it the case that for all values of a variable x, the condition phi is true, or for some value of variable x, phi is true. And importantly, in the dynamic logic setting, we have the box modality, which says that for all reachable states of the program alpha, the post condition phi is true. And dually, the diamond modality, which says that for some run of the program alpha, post condition phi is true. Okay, so using the language of hybrid programs, in previous work published at ADHS last year, we showed how different kinds of switching mechanisms can be modeled using hybrid programs. So here is a very simple example of a switching mechanism. It's known as arbitrary switching. And this can be useful, for example, to model a scenario where the switching logic is not under our control, or maybe it's just unknown, right? So we want to have a safe envelope, and we say that, well, the switching logic can exhibit all possible switching signals. And well, in order to model that as a hybrid program, what we're going to do is, well, we're going to say, let's run a big switching loop, okay, modeled by the star operator in hybrid programs. And in each loop iteration, what we're going to do is we're going to start by picking one of the modes to run. We can pick any of the modes. And then we run that mode for any duration, as long as we like. And if you think about it, this is sort of an operational or a simulation-based view, right? If you were to write a simulation of a system under arbitrary switching, this is essentially roughly the loop that you would write. Okay. Now for a controlled switching model, or some other controlled switching mechanism, then we can similarly model it using a switching loop as follows. Again, we have a big switching loop over here, and first, in each loop iteration, we start by essentially running a modeled controlled switching mechanism, which picks a mode U, and then the plant just responds by following the given mode U for some duration. Okay. And the point of showing you these two models is to say that, well, switch systems can be modeled using looping hybrid programs in DL. And what that means is if we want to state and prove properties about switch systems, we can accordingly state and prove properties about these looping hybrid programs. Now, the property that we're interested in for this talk is going to be uniform global pre-asymptotic stability, or UGPAS. And in the interest of time, I'm just going to focus in on the uniform stability part of this specification, leaving the rest of the paper. So intuitively speaking, uniform stability essentially says that if the system starts close to the origin, then it must stay close to that origin. Okay, and mathematically, what it says is for all epsilon balls around the origin, there is a smaller delta ball such that if the system is started within the delta ball, then for all switching signals, no matter what signal is allowed by my switching mechanism, if I follow that switching signal, I might exit the delta ball, but I'm guaranteed to stay within the epsilon ball. Okay. And this particular mathematical definition, well, it can be translated into a specification in DL as follows. Again, I'm just syntactically writing down the quantifiers that I talked about before. So for all epsilon, there is a delta such that whenever I start inside the delta ball, then here's the important part. Using the box modality of DL, I can quantify over all possible switching signals for alpha. For all of those switching signals for all of the loop iterations, it is the case that my system stays within the epsilon ball. Okay, so now that we have models of switch systems as well as their stability specifications, we can think about how do we go about proving those stability specifications. Now, of course, the thing to do is to first look at what's available in the controls literature. And for arbitrary switching, the canonical technique is to use a so-called common Lyapunov function. And if you're familiar with stability for differential equations, this is just a generalization of it to arbitrary switching. Essentially, instead of having the conditions for Lyapunov functions hold for just one differential equation, we want it to hold for all of the differential equations involved in the switch system. Okay, now we can look at this from a different perspective, from the verification perspective, and we're going to look at it using the idea of a loop invariant. Okay, so here's how a loop invariant works. What it says is, well, let's say we start from inside the delta ball. Okay, the point is that within this delta ball, the delta ball is contained within this blue sublevel set of the Lyapunov function v less than w. And what that means is, well, in my initial state, I'm inside this blue region, which is the invariant. Now, furthermore, thanks to the conditions on the Lyapunov functions, which we know from controls, namely basically the derivative is non-positive, then if I run the loop body of arbitrary switching, meaning I pick one of the ODEs and run it for some duration, then I'm guaranteed to stay within that invariant. Okay, I'm staying within the blue ball. Now, but again, I can repeat this argument. If I'm within the blue ball, I run the loop body again, I'm going to stay within the loop ball, and so on and so forth. And what that means is this invariance is preserved across all of the switching loop iterations. And so it can be used as a means of justifying stability. And in particular, in our proofs in the paper, what we show is that it allows us to syntactically tie together the stability specification and the reasoning about the arithmetic and the hybrid programs and the arithmetic conditions that we know that we need to hold for the Lyapunov functions. Okay, so what we have seen so far is essentially a way of soundly deriving these proof principles for arbitrary switching, and this will later on allow us to implement this within KeYmaera X. Now, however, a more important thing that we can now do is to apply the same concept on a different switching mechanism. So let's just say we have a user-provided controlled switching mechanism. Okay, we can do a very similar thing with the deduction, again using a loop invariant to tie together reasoning about stability with hybrid programs and arithmetic. And importantly, now we can derive correct by construction conditions that we need to hold on the Lyapunov function, even though this control mechanism can be, something that is non-standard, not one of the ones that we a priori know the conditions for. Okay, and that brings me to the implementation. So what we have done is we've provided a new package for switch system stability modeling and proof in KeYmaera X. Users can model switch systems in a graph-based prototype language, and what we do is we can visualize that system over here, and also we can now automatically generate the model as well as stability specification as shown in this box over here. Now, given such a model, we also provide proof automation for those models in the sense of, well, users can either manually put in their Lyapunov functions, or we can automatically search for Lyapunov function candidates using well-known sum of squares techniques. Okay. In either case, well, given such a Lyapunov function, KeYmaera can then automate the rest of the stability proofs using the idea of invariance that I talked about earlier. Okay, so additionally, in the paper, we actually show that this approach can be applied to justify so-called non-standard switching designs. We have actually 3 case studies. For example, we have the case study involving the nonholonomic integrator, where we kind of need to switch between two different controllers depending on whether we are inside an applicable region or not. We have a model of longitudinal flight control, which uses a non-customary Lyapunov function. We have a hybrid automaton model of a cruise controller, which has a lot of modes and transitions between them. Okay, so and I'm leaving sort of all the details to the paper. So to summarize again, this picture really summarizes what we're doing in this paper. We're taking concepts from controls and verification, and we're putting them together in order to develop automated support for the modeling and trustworthy stability verification of switch systems in DL and in KeYmaera X. Thank you.